The primary thing we want to get at there is starlight, but in particular of high redshift galaxies. So effectively, when you're studying it in the infrared, you're largely doing the same things as with optical. You're looking at starline galaxies, getting, if you want photometry, just galaxy counts. That gets you a richness, and you can relate that to the mass. Or if you want, if you have a spectroscope on your telescope, take spectra of the galaxies and get their radial velocities and infer a mass that way. Or also within photometric observations, you can go for lensing, look at any increase in light or distortion of shapes, and try to infer the surface mass, and you can deproject that, assume a Navarro-Franken-White profile, and estimate the total mass of the galaxy cluster. Then onto X-rays, you have free emission with the intracluster medium, and there it's proportional to density squared times temperature to the 1/2. If you integrate that over a bandpass, your temperature dependency is even less. So effectively, you're really getting information about the electron density that way. So keep in mind, X-rays gets you density, SC gets you pressure. All right, here's an overview of the Sunyaev-Zel'dovich effect. And in fact, there are multiple Sunyaev-Zel'dovich effects. Here, just 5 are listed. In principle, we're only concerned about the first 2, and at that, this talk is really going to focus almost exclusively on the thermal SC effect. So the thermal SC is shown with the solid lines on the right figure here, and there is some temperature dependence within of the ICM. You see that the hotter you get, the more relativistic your gas gets. You have a different shape from, say, this yellow line. So that's noted with the R, we call them relativistic corrections. Then you also have the kinematic SC shown here, and then you have corrections just the same. So I'll move on from that, but we'll touch on kinematic a bit later. Here I want to go over a bit of history of observations of galaxy clusters. And it'll be pretty brief, but just to give you context of why we study what we study with galaxy clusters. So early on, you really only would have studied galaxy clusters with optical instruments. And surely early enough, you didn't even know that these were galaxy clusters, right? We didn't know whether things were in our own galaxy or outside that. So optical really dominated until you have an X-ray instrument launched. And that's Uhuru in 1970. You didn't necessarily know that when you saw X-ray emission, that was a galaxy cluster. But pretty quickly, they caught on. And Sunyaev and Zel'dovich, who had proposed the SC effect in 1970, originally proposed it just with the Big Bang. And immediately, once you get Uhuru up there, they realized, oh, there's hot gas in these galaxy clusters. This inverse Compton scattering might actually exist within galaxy clusters. So primarily we attribute their 1972 paper. And there isn't too much development until 1990 when ROSAT is launched. That gives you a lot better resolution to not just pinpoint galaxy clusters, but for the larger ones, actually resolve them and get profiles out. Then, around 1999, you get Chandra and XMM. So those have considerably better resolution than ROSAT and aren't used so much in surveys. There are a couple of surveys, at least with XMM, but their strength lies primarily in targeted observations of galaxy clusters. while optical, the SDSS really gets you a lot of new galaxy clusters. And then coming into 2010, I'd say you get a bunch more instruments in the survey. You maintain optical. Infrared now starts to play a role at identifying and finding clusters at high redshift. And SZ, really anywhere between moderate to high, maybe redshift 1. They don't seem to be finding too many galaxy clusters beyond redshift 1. Optical starts to play a role in terms of weak lensing observations. I'd say Hubble to start with the CLASH program, but other telescopes, say Subaru, are playing a role in that now. And I think going forward, we're going to see no one wavelength dominated either in a survey mode or a targeted observation mode. All right, so what are drivers for studying galaxy clusters by the Sunyaev-Zel'dovich effect? Well, early on, when it was just proposed, the goal was just, can we see this? In the 1980s, we had a few papers that claimed to have a detection, but it wasn't really until the late 1980s that you had a solid, robust detection. Soon after that, once we know that that effect is real, our instruments weren't high-resolution SC instruments, and so we had to treat galaxy clusters as spherical cows. And if you do so, and you realize the different proportionalities of X-ray emission or dependency versus SC, you realize that you could actually infer an angular diameter distance, an angular distance to the galaxy clusters. And if you have that, you have a direct distance measure, and you could constrain the Hubble parameter that way. Other motivations to do it are what also remain today: cluster abundances, or cluster counts as a function of mass and redshift in constrained cosmology. Cluster gas mass fraction, that should be close to the baryonic fraction of the universe, minus some depletion factor. Or cluster peculiar velocities tell you something about how these structures are forming, how mass is being accreted. Then, as we look more towards the present, we now have SC survey instruments, which aren't just getting galaxy cluster counts, but also power spectra due to the thermal SC effect. And that can constrain neutrino masses. Similarly, we can go after kinematic SC surveys, probably stacking galaxy clusters. And here you get a non-temperature biased tracer of gas. So when you go down to the lower masses, like galaxy groups, your gas temperature is not that hot, but your kinematic SC might in fact dominate at the survey level. Now, I've crossed out cluster peculiar velocities here and determined H0. Peculiar velocities, I've crossed them out just because the velocities in most galaxy clusters isn't that much. So in an individual observation, you only detect kinematic SC for very extreme velocities, say over 1,000 kilometers per second. But most simulations expect velocities of maybe 200 kilometers per second. So you have to go really deep, and that's hard to do, especially given the wavelengths you want to observe at to constrain kinematic SC. As for H0, the Hubble Key program really blew everything else out of the water, and galaxy cluster people just left that one alone. We're not going to do better than them. Okay, and here just is showing some cosmological constraints you get with galaxy cluster counts. And here they're showing some previous papers where they had a slightly smaller sample size. And then the priors are basically priors on how you estimate your mass from your SC observations. Do you use a weak lensing calibration or prior, or do you have an X-ray prior to get your mass? And so if you look at the same sample, but just different priors or different mass estimations, you see what the shift is. And I believe V09 would estimate in general lower masses than the weak lensing. All right, so the point is when you're observing galaxy clusters in a survey mode, you don't have very good resolution of your galaxy clusters. So this is the bullet cluster with ACT, and this is the famous picture of the bullet cluster in X-ray, right? You have a massive bow shock, another shock there, but an ACT looks pretty spherical. Is that lack of resolution inhibiting your ability to precisely estimate this integrated Y signal of SC? Are we unable to account for, say, boosts of the Y signal due to shocks? That's a big motivation for going to high resolution where your SC surveys, just think everything's a sphere. Is that actually the case? And that's what we can address with Mustang and Mustang 2. So here I just want to show you what we had before Mustang 1 and Mustang 2. Similar instruments in that they both operate at 90 gigahertz and they'll have the same resolution, but Mustang 2 has a lot more detectors. That array actually is not fully filled with detectors. We have 215 detectors. We have a slightly larger bandpass, but most importantly, our field of view is a lot larger than with Mustang 1. So 4.2 arc-minute field of view versus 42 arc-seconds. How do we observe with Mustang? We do on-the-fly mapping, and in particular, our basic strategy is lucid daisy scans. We can vary the radius depending on the size of cluster you want. We do have some limitations on how fast we can scan due to the telescope and the feed arm. I should note the typical radius that we use is between 2 and 4 arc-minutes. If you include our field of view, you see that we're accessing those typical radii for the galaxy clusters that we're interested in. So 2 to 6 arc-minutes is what I had before. In general, you would like to move as fast as you can across the sky to reduce atmospheric noise, but again, there are limitations of the telescope. All right, so here's one way of representing the maps that we get out, the filtering we do to our signal because of our scanning strategy. So here in the yellow shows Mustang 1's transfer function. Blue shows our default data processing, the transfer function we get out. And green shows a new method of data processing which is still being developed but has some early optimistic results. And the thing to note is this x-axis is in wave number, so it's the inverse scale that you're looking at, but I have marked here the field of view of our instrument and say the full width half max of ACT. And so you notice that, field of view of Mustang 1 here and field of view of Mustang 2 there. Mustang 1 really didn't recover signal beyond its field of view. Same with Mustang 2, at least with our standard reduction, is not recovering that well signal at our field of view. But with our newer data processing, we're recovering quite a bit of signal at our instantaneous field of view. Here is a map seen with 3 different instruments. So Mustang 1 is in red, Nika in magenta, and white is Bolacam. And the point is that with an instrument that has only 42 arcsecond field of view, if you're observing the same galaxy cluster, you end up filtering a lot of the signal, right? We only have marginally significant detection in the very center. Nika 2, Nika 1, had a 1.9 arcminute field of view, and you see they're recovering about those scales, 1.9 arcminutes. Then Bolacam, 8 arcminute field of view, isn't recovering, say, the full 8 arcminutes on this map, or at least not to a significant level, but they're recovering a much more extended signal. All right, so now that we've reviewed Mustang, how we observe with millimeter cameras, getting back to improving our mass estimates of galaxy clusters. At least with Mustang alone, if you looked at that image, we won't be able to really estimate the mass with our data alone. But if we combine it with other instruments, we can. So, a bit down the road, I'll show that we combined Mustang 1 data and Bolacam and recovered integrated Y measurements that way, compared it, or had our own YM relation there. But even if we can't reconstruct the entire galaxy cluster profile with Mustang itself, we are recovering a map of substructure effectively. For filtering out the bulk, that's the same as saying you're left with a substructure map. Can we relate the substructure that we see with any deviations from a YM relation? And to go over a bit of the theory, why we might expect that substructure again, I said before, you have shocks, maybe that's what's going on. Here are a couple of theory papers that are showing you basically the evolution of an integrated Y signal with time. On the right, it's actually integrated Y versus time on X. On the left, they've done integrated Y versus M, and they're basically showing you an expected YM relation evolution in the dotted line, and the solid lines actually trace the evolution through numerical simulations. And the thing I want to point out here is you see that there is a pretty pronounced bounce of integrated Compton Y signal early on in the merger. It then drops back down, and then as the matter and baryons virialize, you see that it'll gradually increase. But it doesn't, this actually should be a 1-to-1 mass ratio in this plot, but you see that it doesn't get to 2 times the initial Y. All right. So what do we find with Mustang and Bolacam? Well, we were able to produce this YM relation and compare it to an expected one from the literature. There isn't great agreement, but we found no clear correlation with substructure in our maps. Here I've color-coded by the dynamical state of the galaxy clusters, which were determined in the literature. This is a well-known sample, the Clash sample. In the end, I'd say we came up empty-handed. That substructure, we don't see an apparent correlation between substructure and scatter in the YM relation.
The mass came from hydrostatic equilibrium, X-ray?
It came from X-ray measurements. It was done in the literature. We didn't recalculate the mass. Okay. So, to go into substructure a bit, if we look at, say, RxJ 1347, which is a well-known, well-studied cool core cluster with a southeast enhancement that looks to be a shock, we see that by some measurements, if you really assume a spherical cluster, and depending on the central you use, you could say that the shock accounts for 9% of the total Y. However, a more recent work actually looked at this and said, well, if you fit an elliptical model, you actually see no significant residuals. So the point is, even when you have a pretty recognizable shock, it doesn't account for that much signal in the integrated Y. And this is not necessarily an upper limit on how much you get, but it's a good starting point. The point is, we don't see that much scatter just due to a shock, at least. All right. Then, to go even beyond that, a cluster that I'm working with recently is Zwicky 3146. It's also a relaxed cluster. No shocks are seen in it. And here, if we fit just a spherical model, we find that whatever residual Compton Y, little y is left, or integrate that and get a residual Compton big Y, it's 1% of this total Y. All right, so we don't see a clear correlation between substructure and scattering the YM relation. So is there something more we can do to refine the YM relation to thereby get more accurate masses? Well, one thing to consider is including ellipticity in our measurements. One recent work showed that even though on your produced sky map you see something that clearly looks elliptical, when you actually go through the motions of fitting a spherical cluster versus an elliptical cluster, you actually don't get a big difference in chi-squared. So your ability to mandate that it has to be treated as an elliptical cluster is still pretty weak. That was done with Nika too. But a lot of the clusters we see with Mustang 2 do not so far mandate the treatment as an elliptical cluster. Still, this might be something to consider. Ultimately, we'll want a pretty large sample to really tackle that question. But it is theorized from numerical simulations. The other thing to do, aside from just looking at our integrated Y measurement and trying to correlate that with something, is revisit mass estimations. It is part of the YM relation, and it's not without its own scatter. And to emphasize that, with my current investigation of this one relaxed cluster, I looked through the literature to see the variety of mass estimations we have. And so here, I'll go into the numbers a little bit, M2500, M500, M200. These are all defined with respect to the density contrast to the critical density of the universe. So M2500 is the smallest mass. It is defined by R2500, which is the smallest radius we care about. And interior to R2500, the average mass, or the average mass density is 2,500 times the critical density of the universe. Or you can play that game at 500 or 200 times the critical density of the universe. So 200 will be the smallest density contrast we tend to care about, and that's your largest mass. Okay, so theorists perhaps favor M200 a little bit, but they also tend to display M500 now. M500 then being a little bit more universal between both theory and observational. This table has been completed with some M500 number for all these papers, sometimes taking just a rough heuristic to go from M2500 to M500. And you see a pretty large scatter early on. Granted, the uncertainties are pretty large. And as you get on, the scatter becomes a bit less, and certainly the uncertainties drop. Now,
So
another way...
Would you define M2500 and M500 because intuitively it's going the wrong way?
It takes a little bit, but you just have to realize that it's the density contrast. So
Oh, I'm sorry. Okay.
it's
Yeah, gotcha. Thank you.
yeah, the center of your cluster has the densest stuff. Okay, so here though, I want to just highlight the measurements that have uncertainties less than 20% of their estimated mass, which will be a bit easier to read than this very long table, but it's there to emphasize really how well it's studied and yet the scatter we see. Now if we look at just the ones that claim to have better than 20% uncertainties, this is what we get. And I've divided it also by X-ray, SC, or weak lensing. So X-ray and SC are both looking at that intercluster medium, the gas between the galaxies. So it'll depend perhaps, quite likely, on the dynamical state of the cluster. Weak lensing really just cares about the mass that's lensing background galaxies. There it depends on how you treat your background galaxies. And interestingly, both of these results use Subaru data, but this one also has wide field imager data as well in it. But the Subaru data is the dominant constraints for both these sources. So I'd say rough agreement with X-ray and SC, and maybe agreement with weak lensing. This is kind of an interesting result. Now, what can we do with Mustang data? So, that is, how can we estimate mass from our data? The canonical method with intercluster medium is to assume hydrostatic equilibrium. And to do that, you'll need to know both pressure and electron density, which is to say, from SC data alone, we can't quite do that, or you would have to assume some electron density profile. You'd have to assume something else. This is another way of making a slightly different assumption with just SC data. So we can actually assume the virial theorem and then assume some mass profile and gas fraction. So that's a way to go between a mass profile that will constrain and effectively an electron density profile. Then a third way we can do it is using the YM relation itself. Basically just a double check on that. Does it give us a mass that we believe? Here's just roughly what it looks like. You constrain those two powers, a slope and a normalization. Okay.
You assume no scatter, I guess, for the last one.
We do include a systematic based on the errors that the YM relations report.
But not an intrinsic scatter between mass and Y.
Well, often they report their uncertainties based on the intrinsic scatter. Okay, so how do we go from a map, say on the upper hand, to a pressure profile? There are a variety of methods, but I'll go straight towards the one we use. Basically, we assume some geometry, often it's spherical. We integrate the pressure along the line of sight. That can be done, obviously, numerically. There's also an analytic way to do that if your pressure profile follows a power law over some region. And then we have to, aside from just integrating that, we have to account for our transfer function. The plots I showed earlier, where Mustang 1 has a transfer function that really drops off at large scales. Mustang 2 does a lot better, and Ninkasi better yet. So, from that we can run it through, apply MCMC or whatever you want, but MCMC is really the best, simplest way, I'd say, to get at it. And you can constrain your pressure profile that way. Here I'm showing results from 2018 paper where I'm comparing pressure profile results from Mustang 1, Nika 1, and Bolokan, and showing agreement across these three instruments, which are sensitive to different spatial scales. Right? It's not clear that your instruments necessarily are going to agree across that range, but in this case, we do see agreement. All right. Then I want to go back to the fact that Minkowski really is a promising way of analyzing our data insofar as we shouldn't need to account for a transfer function. If we have results, at least as we do for Zwicky 3146, we have no effective, or we have a transfer function of 1 everywhere effectively, except for the 0 mode, we don't have a mean level constraint. But on other spatial scales, we think we can do really well and recover quite far out. Here's just going into how that works. Rather than doing a typical common mode subtraction, which the idea there is you're on the source, off the source, and what you see in common is the Earth's atmosphere, you can just subtract that out as a mean across all detectors. Rather than do that, we characterize the noise in Fourier space, but before we do that, we actually rotate it in SVD, which accounts for correlations between detectors. And so, as long as we believe that noise model in Fourier space, we basically do a maximum likelihood fit there, and what we get out should be the galaxy cluster or whatever astronomical signal we want. Here is a comparison of the results that we get for Zwicky 3146 if we do our canonical data reduction, which we call Midas, or if we do Minkowski. Here you see that there's substantially less signal, and we get even a little bit of bowling. And that's just the filtering effect that we get, or a transfer function. But here, with Minkowski, you see effectively no transfer function. Now, what does that mean for getting science out of it? Well, the first science step is to get a pressure profile, and I'll compare for you what we get from Minkowski or from Midas. Now again, Midas, we know a transfer function, so we apply that. So we're not completely lost with Midas. We're able to recover quite well, except out right at the field of view. This is the radial field of view, where we see a bias being introduced. That's effectively saying that our constraints on our transfer function aren't that good. We don't know our transfer function at that radius, at that wave number that well. But Minkowski looks really promising from this result. And here we can see a comparison to XMM results, which, sure, I suppose you could argue that XMM might not be the right answer, but I take that as quite encouraging. All right, then what do we get for actual masses? Here I've calculated both M500 and M2500 for a variety of methods I showed earlier. And I want to then focus on the M500 numbers, where I'm assuming a YM relation, and I've done 3 different YM relations to kind of show how they compare. I'll include a systematic due to their intrinsic scatter as the second uncertainty. The last uncertainty is a systematic due to our calibration, and the first is our statistical uncertainty. I'd say you see rough agreement between all of them, although this second YM is consistently biased low. And then we see this virial theorem is biased high. But between YM1, YM3, and hydrostatic equilibrium, I'd say you have pretty good agreement. I'll also note that your uncertainty is pretty large here because in the top model, it's what I call the non-parametric model. So I'm not assuming a shape of the pressure profile, whereas I am down here. And that just means that at that last bin where we're getting up to R500, our constraints begin to be weaker. And that's largely a function of our scanning strategy. We did not spend that much time out at R500. You could be concerned about how well Minkasi does with recovering those larger scales. But I would say if we had a slightly larger scan pattern, I think the uncertainty would go down a little bit more, despite the fact that you're spreading out integration time a little more. All right. Then I can also show you this in context of the plot we had earlier. So now Mustang 2 has the crosses. I'm showing you the statistical errors with the first error bar, and then with the addition of systematics here. Again, you see good agreement between all our mass measurements that are from the intracluster median. We can touch briefly on that. I think it's interesting to note such small error bars before in the literature. Those only quote statistical, but they're also artificially small due to an assumed pressure profile shape. And in fact, I think these later points include the same data. So it shows you just what you actually get when you're assuming a pressure profile shape versus doing something agnostic of the pressure profile shape. All right. Now, I want to also get to what differences should we expect between weak lensing and any mass measurement from the ICM, in particular when you assume hydrostatic equilibrium. The main bias that is proposed between hydrostatic equilibrium and a weak lensing measurement, well, it's called the hydrostatic bias, but it's dominated by the fact that you assume your pressure in your hydrostatic equilibrium is only due to thermal pressure. So if you have non-thermal pressure in your galaxy cluster, you'll have, well, unaccounted for pressure support, and you'll have unaccounted for mass. So you should be biased low in your mass measurements from the ICM. Interestingly, even with this result, it's not clear that we're biased low. So that would indicate that we have very little non-thermal pressure support in this galaxy cluster. I'd say at an interesting level how low it is. We tend to expect on the lower end about 10% non-thermal pressure support. It's an average from, well, within R500. But you can get even more than that at R500. So here are some simulation results from Battaglia 2012. And you see that at R500, your non-thermal pressure support, here shown as kinematic pressure, rises to roughly, well, maybe not quite 30%, but close to 30% around R500. And here, basically, these are all clusters at redshift 0 at different masses. Here you have a given mass or mass range across different redshifts. In either case, you see pretty similar non-thermal fractions. All right. So what do we say? Even if we look at these YM relations, depending on how they're calibrated, one of them is calibrated from a weak lensing catalog, another from a numerical simulation. Either way, we would think that these account for all the mass. But in fact, they're not clearly above the other estimations, where this YM scaling relation actually is based on hydrostatic equilibrium masses. How is that? I find that pretty interesting. So I think there's definitely room for everyone to improve their masses. I would say that one definitely needs some work. But the point then is, in order to improve our mass estimation, we can't just say, oh, reduce the scatter in your YM relation, because in doing that, you're hiding whatever systematics are within your study, right? But that's great that this has no scatter, but the fact that the result we get from this YM relation differs from that one is telling us there are other uncertainties we need to account for. And this one is a simulation paper in red, and then it's showing two observational studies, both that include weak lensing, which, okay, there's a lot of scatter, but it's important to notice you're not automatically better just because you have low scatter.
The central panel came from Arnaud or Prat et al.
This is Arnaud, 2010. This is Planel's.
That's well, the Boffic, the abscissal ordinate of the central panel, okay, are derived from the same quantity. So there is the scatter is along. I wrote in my paper. The scatter is along the line, so you don't see the scatter because the scatter is along the mean relation.
Right. So they assume already an X-ray relation, which is
But that's induced the scatter in that way, so you don't see the scatter.
Right. Okay. So there's definitely work for everyone to do it, but I would say we don't automatically know how much non-thermal pressure support there is just by having a weak lensing mass and an X-ray mass. We need to really trust both of those masses first before we say, aha, there's non-thermal pressure. In fact, a lot of studies even show basically that X-ray getting, or ICM getting higher mass than weak lensing. Well, that's unphysical as far as I can tell in this paradigm. So we're not quite at a point that we can just take lensing and ICM and be done. Which is to say, it's good to have other ways to measure or estimate the non-thermal pressure support. Can we do that with SC? Well, yes, at least we think so. There are a couple theory papers, and there's a preliminary observational paper from Cautry and Gaspari that used Planck data and basically went through the motions of what we think we need to do to constrain, turbulence. And first, we do that by constraining pressure fluctuations. So the idea is that if you take whatever residual delta P you have, divided by your bulk model, that's your delta P over P. If you take a power spectrum of that, the slope of it tells you about thermal conduction, and the amplitude tells you about the amount of turbulence you have. Here's just a power spectrum in Y space, Compton Y, and then they'll use a window function to deproject that to pressure. But basically, you're getting an idea of the pressure fluctuations this way, and ultimately, that's the goal we want to do with Zwicky 3146. So now that we've gotten a nice constraint and shown that, our masses are in rough agreement with X-ray, the next step is to go and look at pressure fluctuations. All right, here's just a bit of a preview. We don't actually have a map of pressure fluctuations just yet, but a Gaussian gradient magnitude is a bit different, but it gives you perhaps some ideas of structure within the cluster. We see a little bit of structure in the core. That's maybe not too surprising. It is a cool core. It need not be exactly a sphere from 0 to R500. Here's some X-ray images, and here if you subtract out the spherical image, you also see a bit of structure there. So my expectation for pressure fluctuations is we might see a little bit in the core, but the central or moderate radii, I think we'll see very little pressure fluctuations. All right, So if we look beyond just pressure profiles and mass estimations, what can we do with Mustang? Well, I think there's quite a bit we can do. There's a lot of physics going on in the ICM. Here demonstrates a short list of what we know is out there. Again, there are a few radio aspects that we could investigate and try to associate with shocks or other pressure features we might see, other substructure. In any of these cases, we don't strictly understand the generation of these cosmic rays. How do they get accelerated? Certainly we have ideas. Diffusive shock acceleration would be one, but you really want to find a shock front in the SC and then see how that aligns with your radio image. Other things we have are X-ray cavities. So clearly there's a gas that's not as dense in order to have a cavity, less X-ray emissivity. Sloshing, what's causing that? Can we constrain it with SC? All right, shocks we can see in SC, but can we do more with that? Cold fronts are a feature we definitely see in X-ray, but we should expect them to be roughly in pressure equilibrium across the front, so we likely won't see them in SC. All right, as for shocks, just to demonstrate again the power of SC, here was work from Mustang 1 where we saw a shock which had initially been overlooked in X-ray, but when you go back to the X-ray data and you know the region to look for, you in fact find consistency that yes, there is a shock, and we can constrain Mach numbers after the fact, given the region of interest from SC. If we look to perhaps a more prominent shock, we might be able to do better than just constrain the Mach number. We might actually be able to constrain the temperature. Now, we would need X-ray data, but that exists. In fact, quite a bit of it. And the interest here in constraining the electron temperature is understanding the heating mechanism of the gas. So we don't know if the gas is heated instantaneously or through Coulomb collisions. And so far, the data doesn't provide a good indication of which model is preferred. Now, X-ray data, there's even more X-ray data than this paper. You might say, what good does SD do given this additional X-ray data? There are two big things. First of all, the X-ray has a difficult time constraining the pre-shock temperature because the density is lower. X-rays could also potentially be biased or not correctly recovering the temperature when it's a very high temperature, just because of their bandpass. It's not sensitive to those high temperatures. So SC doesn't really care about the temperature. You would have to account for relativistic corrections, but those are small compared to the systematics that X-ray faces at high temperatures. And thereby you can say whether you're consistent with the current X-ray constraints on temperature, or say no, the X-ray seem to be systematically biased high or low. And all of that really is important because there aren't many systems that we have the resolution to constrain how it's heated over time behind the shock front. Aside from shocks, we also have X-ray cavities. We don't know what's supporting these X-ray cavities. There's clearly some pressure support mechanism, but the lack of X-ray emission really doesn't yield too much information from the X-ray data. So from SC, we might be able to gain some insight. And there is already a 2018 paper from Karma. They had quite a bit of time, I think around 100 hours. In fact, Chandra also has over 100 hours on theirs. But you see with 16 hours of Mustang 2, we get a similar map. Definitely not quite the sensitivity at 16 hours only, but I'd say we're doing really well for just 16 hours compared to 124. And here's a comparison of the signal we would expect in SC depending on the pressure support mechanism. So our sensitivities, by the way, tend to be in microkelvin. We get 50 some microjanskis per beam within an hour. So if we have 16 hours, you see that we should definitely be able to distinguish between most of these support mechanisms. If it's down to these two, that might be tight to distinguish between. All right, and then I already touched on radio features and associating them with shocks. So I'll move on then to just say beyond Mustang 2, where Mustang 2 we only have one band, what else can we do with SC studies? Well, I had set aside kinematic SC. Because the thermal SC is dominant and you have different spectral signatures, you need at least one other band to disentangle kinematic from thermal SC. And this informs bulk motions, be it within the cluster or the cluster as a whole. You also have relativistic SC corrections, which are also going to be generally pretty faint, but it'd be nice actually to see a case where for a high enough temperature and deep enough observations, we should actually be able to constrain the electron temperature just from SC observations. There's also a non-thermal SC that touches a bit on those X-ray cavities. What's the pressure support mechanism? So if you have the spatial resolution and you know where you are expecting non-thermal SC versus thermal, Mustang 2 or a single band is okay. But if you don't have that spatial resolution, you'll need spectral resolution to disentangle that. And for all the components you want to separate, you need that one more additional band. So potentially you're looking at an instrument of many bands to tackle all these different effects. But even with just two bands, getting the kinematic is a pretty good next step. But I want to then return to thermal SC and Mustang. SC studies, especially thermal SC studies, have been relegated just to bulk observations of galaxy clusters. Just get an integrated signal from that cluster and see what you can do from that. But now I think with the advent of these high-resolution instruments, especially Mustang 2, we're not just relegated to determining the integrated Y signal and estimating a mass that way. We can actually estimate a mass for ourselves and see how that compares with the literature. We can also look at pressure fluctuations and start to compare mass estimates from pure hydrostatic equilibrium versus accounting for non-thermal pressure support and see how important non-thermal pressure support is. We can go even beyond just non-thermal pressure support and look at shocks or, well, I guess a different version of non-thermal pressure support, cosmic ray support. Does that exist for X-ray cavities? For any of these SC studies, Mustang 2 and GBT is a very powerful tool for investigating it. And I think we've got a few more years to really showcase that.
Questions for our speaker?
Here's a short one. What is a radio phoenix? What is a radio phoenix?
Yeah, so the idea of a radio phoenix is that perhaps a shock came along a billion years ago and produced a population of cosmic ray particles, but they are at some sub level where they're not able to produce synchrotron radiation there, and you just need a little more acceleration to get them back up to producing synchrotron radiation. So, yeah, I know the least about how that comes about. I think it's a pretty open question.
You go to the image where you showed the two deficits. Go forward a little bit. There.
This.
The cavities. That's.
Yeah.
Have you looked at all whether their jets sort of lined up with those
Yeah.
cavities?
There. I wonder if I have an image. There's a pretty nice image that shows the jets lining up with it. I probably don't have it here. Okay, but there are jets that line up. It's not exactly in the center. Let's see if I can move it well. The jets almost stream more vertical that way and vertical down that way. Or even here where the lines guide you a bit more. The jets don't go exactly out from the center. It goes down that way, and then there's a little diagonal in it. So, I think, yeah, that could be interesting too, but the first thing is just to approximate those as spheres and then see what signal we get and constrain the pressure support that way.
Any other questions for our speaker?
Usually whenever I think of non-thermal support or emission, I think of magnetic fields. Can any of this non-thermal support, do you have magnetic fields somewhere here? Okay. And that answers my question. You can sort of trace the intercluster magnetic field with these decrements?
Yeah, I'm not sure if we would consider it to be, well, we shouldn't consider it to be representative of the whole intercluster medium, right? It'd be localized to the bubble. I don't think, as far as on a global level, I don't think magnetic support is expected to be that dominant. Basically, the order I understand is thermal pressure support, non-thermal being turbulence, potentially some rotational support, and then maybe after that you're looking at some magnetic.
Any last questions? All right, this lecture was good.
My confidence. It's very nice, right? Very nice presentation. Prepared in a way that even the people that don't work on the subject understand what's going on.